Alright, AP Physics C midterm review sheet solutions. I'm going to skip over this first part here. I might make a separate video filling those out, or I might just fill it in and post it. I want to get into the problems here because it's probably where most people are going to jump into these. So, rocket launches off the ground with an acceleration of 15 meters per second squared, an elevation of 3 kilometers. The booster shuts off, and the nose cone of the nose capsule of the rocket attaches from the booster, instantly gaining 50 meters per second of extra velocity due to the conservation of momentum. Now, like I said in class, that due to the conservation of momentum, that's just a note. That's not really anything important to do with the problem. The capsule is then in one-dimensional projectile motion. You may assume that the acceleration due to gravity is constant throughout this flight. Alright, so draw a diagram of this flight showing where the acceleration changes. Now, I left a pretty big amount of space here because I do want you to use this, you know. I tried to tell you a few times that these diagrams are important. So it starts off at rest, fires upwards, right, gets up to, let's say that's the 3 kilometers or 3,000 meters. The acceleration during this time interval, he said, was plus 15 meters per second squared. Alright, so we're going to have to find the velocity at that particular point. It said VF here, but I guess that doesn't particularly matter. Now, blasts off, it's going to accelerate at that rate for a distance of 3,000 meters, and then it's going to achieve some velocity by that point. Once the booster turns off, it is now in projectile motion. It's just like being thrown up into the air from this elevation at whatever speed it was at when it got to that elevation. So at the peak of the flight, the apex we call it, the V is 0 meters per second again. Alright, now this would be a nice one to solve in terms of energy, right? If you could figure out the speed there, then you could say, okay, 1/2 mv squared equals mgh. You find the height that way, above that 3,000, but unfortunately, we don't have that in our tool belt yet. You guys know how to do that probably, but we're not quite there yet. So the acceleration during this part of the motion is less, and it's negative 9.8 meters per second squared. So kind of a two-step problem here, right? This acceleration changing, this is a boundary here, right? We're at this point where the acceleration changes, that's a boundary. And there's conditions at that boundary. Whatever the speed is here is the final speed for the first interval and the initial speed for the second interval. So that's a boundary condition, that speed at that height. So let's see, so we need V final here. This is going to be a classic V squared or timeless equation problem. This is V naught squared plus 2a delta x. Delta x in this case is going to be the height, right? So V is radical. This term is 0, starts from rest. 2 times 15 meters per second squared times the elevation change of 3,000 meters. All right. Radical should be over a little bit farther, I suppose. So now we plug that into our calculator, get the your square root of 2 times 15 times 3,000. That's VF, about 300 meters per second. So not terribly fast for a rocket. That equates to about 650 miles per hour, something like that. So, you know, fast but not crazy. Perhaps it's a model rocket. Anyway, from there now, right, so we know that that is 300 meters per second at that boundary. Now that becomes our initial velocity over this time interval, and the final velocity is 0. So we are looking for, you know, this vertical distance here. And we'll add it to the 3,000. So that vertical distance, delta y, I guess I should say, maybe I should have said delta y down here, it doesn't really matter, I suppose, is what we're looking for. So let's see. another v squared equation. V squared equals v naught squared plus 2a delta y. V naught squared in this case is 300. V final squared is the 0. So 0 equals 300. And the signs do matter here, so be careful. 300 meters per second, that's going to be squared, plus 2 times negative 9.8 meters per second squared. Delta y is our unknown. So bring this over here. 300 squared is going to be, what, 90,000? I suppose it would be negative, or I could just drop the negative sign from over here. Right? This is going to be meters squared per second squared. I suppose I should show all the units here. Divide by 2 times 9.8. Alright. Delta y over this time interval is 90,000 divided by 20, or 2 times 9.8. It's about 4,600 meters up, and it is positive. You can see what the units would be, right? The second squares would cancel there. 1 of the meters would cancel on the bottom, leaving you meters on top. So h, right, that's going to be your total height, right? That is going to be the 3,000 meters plus the 4,600 meters, so it's going to be 7,600 meters for the final answer. Oops, went off the page. All right, so it's just a nice basic motion problem, boundary condition type deal. I like that one. All right, this one we did in class, so I'm going to really blast through this one pretty quick. So there's our position function. My daughter making noise in the background. Dx dt, the derivative of position with respect to time is velocity. So it's the d dt of negative 2t cubed plus 15t squared plus 20t. Alright. So we've got, bring the 3 downstairs. Negative 6t, take a power off, squared. Bring the 2 downstairs, 30t, take a power off, take a t off, plus 20. Alright? So then, there's our velocity function until it reaches its terminal velocity. Oh, thanks, babe. The acceleration function now. Alright. That acceleration is going to be derivative of velocity with respect to time. Alright, so we're going to take another derivative here. So it's going to be, bring the 2 downstairs on that function up there. Alright, so it's negative 12t plus 30. Alright, so that's our acceleration function. I'll just rewrite it again. Notice I didn't put the full notation here. I didn't do this part like I did here. That's okay. Part C, determine the magnitude of the object's terminal velocity. So remember, V terminal is when the acceleration is 0. When all the forces are balanced out, right? The force of gravity is getting canceled out by whatever the drag force is. So if it's air drag, whatever that might be, terminal velocity is when those balance out and it's no longer accelerating. So V terminal when acceleration is 0, so we put in 0 for A, it was negative 12t plus 30. You'll never reach terminal velocity if one of these don't have the opposite sign, right? The force always has to be opposite the motion. So the 30, that's your initial acceleration, so to speak, or your initial velocity. The change has to be opposite that for it to ever end up at a constant velocity. Anyway, all right, so 12t equals 30, divide by 12, divide by 12. T is 30 over 12, which is 2.5 seconds to reach terminal velocity. Then you take that time that we reach terminal velocity and we plug it in to our velocity function. So we know when the acceleration is 0, that's 2.5 seconds. So now we take that, put that into our velocity function, figure out what the speed is at that time. Now, after that time, this function for the velocity no longer can be applied. Once you reach terminal velocity, v is constant. So this is the velocity function up until terminal velocity. Once you reach terminal velocity, the velocity is just constant. So at 2.5 seconds, I'll plug that into my calculator here, -6 times 2.5 squared plus 30 times 2.5 plus 20. It's about 58 meters per second, the terminal velocity. And usually they put a capital T to represent terminal velocity. All right, there's that one. All right, I'll do this angular velocity one, and then I'll start a new video, second video here, so they don't get too long, kind of break it up into the different types of problems. Drive motor rotates a disc initially at rest with an angular velocity function as given below, where omega equals 4t squared plus 2t. The function gives units of radians per second for angular velocity. Determine the magnitude of the angular velocity of the disk after 4 seconds of rotation. So that is the angular velocity function. So to find the velocity at 4 seconds, we're just putting in 4 for t. And don't get too hung up on the units here. We know that this gives radians per second, so these constants have to agree with that. So this would be radians per second cubed. The units on this would be radians per second squared. We'll be in good shape. So 4 times 4 squared, I guess that would just be 4 cubed, but that's okay. All right, looks like we got about 72 radians per second at 4 seconds. So 72 radians per second. So it's 2 pi radians per rotation. So it is kind of interesting sometimes to think about how many rotations that is per second, right? So if you divide that by 2 pi, or about 6, that's about 11.5 rotations per second. So that's pretty fast, Multiply that by 60, that'd be about 700 RPMs. That's actually pretty slow when you're talking about car's engine, but anyway. Determine the magnitude of the angular acceleration of the disk after 4 seconds of rotation. All right, so angular acceleration, we have to do some calculus here. So alpha is the derivative of omega with respect to time. And remember, this is acceleration. Acceleration, whether it's linear or rotational, it's always the derivative of the velocity with respect to time, the rate of change of the velocity. So angular velocity or linear velocity. Don't get hung up on the word angular or rotational. Just read it as acceleration and you'll be in good shape. All right, so derivative of this function is 2 times 4 times t, subtract 1 off the power, so I don't know why I'm showing the whole power rule, but oh well, the positive one is down in front here. Alright, so it's 8t plus 2, so alpha at 4 seconds is 8 times 4 is 32, plus 2 is 34 radians per second squared. Great. Now, determine the magnitude of the angular displacement of the disk after 4 seconds of rotation. So, displacement is always, no matter if it's linear or rotational or angular, whatever you want to say, it's always the derivative of your velocity function with respect to time. The integral of your velocity function with respect to time over the desired time interval. Alright, so we just put our function in there from 0 to 4 seconds. That's our limits of integration. Alright, so 4t squared plus 2t dt, so with respect to time. So we take the antiderivative. When we take the antiderivative, we're doing the derivative in reverse. We have to raise the power 1 and bring that new power downstairs. So 4t cubed over 3 plus 2t squared over 2, evaluated from 0 to 4. Simplify that a bit, so it's 4 times 4 cubed over 3 plus 4 squared. Technically minus 0 because that's what you'd get if you plugged in the bottom limit. So the distance here, okay, so 4 times 4 cubed divided by 3 plus 4 squared is 101 or 100 radians. And the final thing is a kinematics problem using this. Let's say it takes 4 seconds to reach top speed. The drive motor shuts off. The disk immediately starts slowing down at a constant rate of -1 radians per second squared. So it's -1 radians per second each second. So it's at 72 radians per second. So your omega naught is 72 radians per second. And it's got to slow down. It's got to lose a radian per second every second. So it takes 72 seconds. But let's just prove that mathematically. So alpha, that's your angular acceleration, equals change in velocity over time. Alright, so -1 radian per second each second equals delta omega. So the change, so omega final is 0. So it's final minus initial. It's -72 radians per second. It's got to lose in some amount of time. So you cross multiply, you get t equals -72 over -1. You get 72 seconds. All right, so I'll pause there. We got a couple force problems to do here that might take a little longer, or one force problem, I suppose, might take a little longer, and a projectile motion problem that might take a little longer. So I will pause there and start a second video here.